Hey Emma,
What's up, Oliver?
the other day while walking with a friend in the rain, I saw something strange.
Something strange. What was it?
I was closely observing my friend's umbrella and noticed that raindrops were falling off in a spherical shape. Normally, when water droplets fall on a surface, they spread out, right? So why didn't the raindrops on the umbrella spread out and remain spherical?
That's probably because the umbrella was treated with a water repellent coating.
The water repellent treatment, is that different from waterproof or water resistant?
Water repellent is a completely different function from waterproof or water resistant. Water repellent is a function that repels water and keeps the surface from getting wet.
It's fascinating how water bounces off. Repellency sounds interesting. Can you explain it to me in more detail?
Sure thing. So this time, I'll explain the essence and mechanism of water repellency. First, let me explain the difference between water repellency and waterproofing, as it can be easily misunderstood. Water repellency refers to the ability of a surface to repel water. In other words, it refers to the ability where materials don't get wet by water, but instead, round droplets roll off from the surface. On the other hand, waterproofing refers to the function that prevents water from penetrating. It could be said that it functions as a barrier to prevent water from seeping into the interior of the material. By the way, the term water resistant is also used, and it has the same meaning as waterproof.
They are quite similar, so I still don't fully understand the difference between water repellent and waterproof.
Pay attention to the surface's resistance to water. It's easier to understand that way. Water repellency is the ability to repel water, so the surface is less likely to get wet. On the other hand, waterproofing refers to the ability of the surface to get wet, but without water penetrating to the other side. Glass is a good example to understand the difference between water repellency and waterproofing. Glass has a surface that's easily wettable, so it has low water repellency, but it doesn't let water through, so it has high waterproofing.
I see. So waterproofing means that the surface doesn't get wet. Based on what you've told me, it seems like water repellency is more superior. So being water repellent means that the surface doesn't get wet and water doesn't penetrate through to the other side, right? In that case, water repellent seems like a superior version of waterproof, don't you think?
No, it's not that simple. The water repellent fabrics do make it difficult for the surface to get wet, and as a result, it also makes it harder for water to penetrate inside. However, there is a major weakness. That is, when the pressure from the water exceeds a certain level, it can no longer repel the water.
What kind of situations would cause high water pressure?
Simply put, it's when there's a lot of water or when water is forcefully splashing. Imagine scenarios like being submerged in water or where water is forcefully hitting you like a wall. Even with water repellency, in these situations, water can't be repelled and easily seeps inside. In other words, items used underwater like underwater cameras need waterproof features. If you need to protect yourself from rain like an umbrella, but want to avoid the umbrella getting wet and heavy, water repellency can be useful.
I see, so it's all about using the right tool for the right job, huh?
That's right. Let's delve a little deeper into the concept of water repellency. As I explained earlier, water repellency is a function that prevents the surface from getting wet. Oliver, what do you think constitutes a surface that is prone to getting wet?
I'm not sure. I can understand it intuitively, but I can't explain it well in words. I wonder what it means to be easy to get wet.
The ease of getting wet is expressed by the contact angle. The contact angle refers to the angle formed between a droplet of liquid and a solid surface it is dropped on. I think it's easier to understand when you see a diagram rather than trying to explain it in words.
Indeed, it's much clearer when you look at a diagram.
The larger the contact angle, the less likely it is to get wet. When we compare objects with different contact angles, it looks something like this.
The object with the largest contact angle I've seen is similar to the water droplets on an umbrella.
When the contact angle is large, it means that the area where the water droplet touches the surface is small, which means it's in a state of repelling water.
I see. I was just wondering, was it necessary to explain the ease of getting wet in terms of the contact angle? I understood the explanation of the contact angle, but personally, I find the sensation easier to grasp. If I can understand it through sensation, then I feel like that's enough.
That's a great question, Oliver. It might go off topic a bit, but it's a really important concept that can be useful in various situations. Let me explain a little about the importance of verbalizing things in an objective manner. It's true that some things can be understood through intuition, but verbalizing them can be quite challenging. However, if we don't put things into objective terms, we won't be able to make comparisons. Because in the world of science, it's required to articulate things in a way that everyone can perceive them.
So comparison is important.
Yes. Let me explain this with an example of water repellency. Suppose there are two materials that are hard to get wet. It's impossible to accurately compare the excellence of different water repellent functions based solely on intuition. And using superior water repellent materials can potentially lead to significant cost reductions. We must compare things with the same properties accurately.
You're right, we can't make a valid comparison based on intuition alone. I understand and agree with you.
That's great. Now let's get back to the topic. The ease of wetting can be expressed by the size of the contact angle. The larger the contact angle, the less likely it is to get wet, and the smaller the contact angle, the more likely it is to get wet, and the type of object affects the contact angle.
Why do different objects have different contact angles?
That can be explained by surface tension. The value of surface tension varies depending on the type of substance, and accordingly, the contact angle also changes for each substance.
Surface tension is the force that tries to make the surface as small as possible.
Exactly right. I explained the mechanism of surface tension in a previous video, so if you're interested, check it out from the description box. For now, if you understand that it's a force trying to minimize the surface, that's good enough.
I understand. But what is the relationship between surface tension and contact angle?
The relationship between surface tension and contact angle is quite simple. It can be expressed by a single equation. Imagine there's a liquid on top of a solid. The point where the contour of the liquid intersects with the solid surface is what we call the endpoint. The forces acting on this endpoint are broken down and the contact angle changes so that the total force acting in the horizontal direction becomes zero. There are a total of 3 surface tensions acting on this endpoint. The first one is the surface tension that acts between a solid and air. Let's call this surface tension G's. Gs tries to reduce the surface area of the solid in contact with air, so it acts in the direction of covering the solid surface with a liquid. In other words, it applies force in the direction of the liquid spreading. The second surface tension is the one that acts between a liquid and a solid. Let's call this surface tension GLS. GLS acts in the direction of reducing the surface area of the solid in contact with the liquid. It exerts a force in the direction towards the center of the liquid. The last surface tension mentioned is the surface tension that occurs between air and liquid. Let's call this GL. The surface area of a liquid is smallest when it forms a sphere. So let's aim for a spherical shape. So, GL works along the tangent direction of the liquid's contour. It might be a bit confusing, so for now, just think of it like this.
I understand.
And when you combine these 3 forces, the resultant force in the horizontal direction will be 0, causing the endpoint to move. If you express this in a formula, it becomes Jek Gukuz at Galkasti LA. This formula is known as Young's equation, and it can explain the phenomenon of water repellency with just this single equation. In the case of solids with high water repellent properties, the 3 surface tensions take values that result in a larger contact angle.
I see. I think I kind of understand now, but I don't really get what it means for the endpoints to move, so that the horizontal force becomes 0. Why are we moving?
I think it would be easier to understand if we focus on the actual force acting at the endpoints. Let's say the angle that is smaller than the contact angle, which satisfies Young's equation. The horizontal forces acting on the endpoints do not add up to 0. Instead, they exert a force towards the center of the liquid. In other words, the liquid surface is pushed towards the center, causing the endpoints to move. And as the meniscus moves inward, the liquid rises upward in response, causing the contact angle to increase. Like this, when the actual contact angle is smaller than the contact angle predicted by Young's equation. The meniscus moves inward, which means that a force is acting in the direction of increasing the contact angle. Conversely, when the actual contact angle is larger than the contact angle predicted by Young's equation, a force is acting in the direction of decreasing the contact angle. Eventually, the contact angle adjusts itself to the angle predicted by Young's equation.
I see. So it adjusts automatically. Speaking of which, waterproofing is such an interesting feature. I understand how waterproofing works, but when I see water droplets in a round shape due to waterproofing, it feels really mysterious.
I also love observing water droplets bouncing off and falling one by one, so I find waterproofing fascinating and enjoyable. By the way, using something called a water repellent spray, it's possible to give various things a water repelling function. The water repelling function weakens the more you use it, so older umbrellas start to lose their ability to repel water. But if you use a water repellent spray, they can regain their ability to repel water.
Wow, that's really convenient.
I highly recommend using water repellent spray on shoes and such. When you're using an umbrella, even if some rain splashes onto your shoes, it won't seep inside anymore.
That's handy. But wouldn't it make the inside of the shoes more humid?
You don't need to worry about that. Water repellency is a surface function that repels water, so the breathability doesn't change much. Waterproofing, on the other hand, has close to zero breathability, making it more prone to moisture buildup.
Oh, I see. Water repellency can be really useful, depending on the situation, huh? Thank you, Emma. I've learned something again this time.
You're welcome. So, let's summarize this time. Water repellency is a function that makes water bounce off the surface. Water repellency and waterproofing may sound similar, but waterproofing allows the surface to get wet without letting water penetrate, making it different from water repellency. The mechanism of water repellency can be explained by surface tension. The ease of wetting the surface is expressed by the contact angle. The contact angle changes so that Young's equation holds true.
I got it.
That's all for now. Thanks for listening to the end. I plan to explain more of these everyday questions like this, so feel free to drop by again if you'd like. So, thank you for watching.
Thank you for watching.